In this part of our training, we'll talk about non-supercell tornadoes and other rotations. A non-supercell tornado is also referred to as a landspout. It has no organized large-scale rotation. There is no wall cloud associated with it, and there is no rotation shown on radar either. This particular example was taken near El Paso in May of 2014. Notice that there is no wall cloud that's associated with this particular circulation. Here's another example from the same area, looking a little more dramatic. It can be nearly transparent at times. Notice that you can see somewhat through it. They often form near a slow moving cold front or a stationary front with opposing wind flow. They can also form on the southwest edge of a cluster of multi-cell thunderstorms. In Illinois, these are most common from late April into June. Here's a video of that landspout that occurred near El Paso last year. Notice how it is very transparent. You can see the clouds behind it. It isn't moving very far, very fast. But it can cause damage if it were to hit something. Another type of rotation that you may see is called a gustnado. This is a short-lived rotation that's along a gust flow or an outflow. This particular radar image, all these blue lines that are coming out from the thunderstorms are what we call gust fronts or outflow boundaries. These are accompanied by cooler air and gusty winds, and these are most likely where a gustnado would form. The rotation does not reach up into the cloud. And once again, we also do not see a rotation on radar. So look for the rotation at the ground, not just dust being kicked up, but an actual rotation at the ground level. These can cause minor damage, mainly from the wind gusts. If you happen to see one of these, be sure to refer to it as a gustnado. Another thing that we tend to see across central Illinois is cold air funnels. They occur in vertically developed clouds, and usually they don't have any thunder with it. They are most common in late spring and early summer, and also again in autumn. Rarely do they touch the ground. Should they actually touch the ground, they could cause some minor damage. Almost always, they occur in the afternoon or early evening hours, and they can persist for quite some time.
Hi there, I'm meteorologist Josh Judge from the Stormwatch 9 Weather Center, and we're taking a closer look at the microburst, which has now been confirmed in Plastow, New Hampshire. And here's a look at the radar loop from yesterday. The microburst has now been confirmed by the National Weather Service of containing maximum wind gusts of 80 to 90 miles per hour. It was 2 miles long and 1.6 miles wide. Now, this is a wide view of that storm rolling through the Plastow area in southeastern New Hampshire yesterday afternoon. But we'll take a closer look here, slow it down for you, and show you the area where this occurred right around here, right around Route 108 in particular, also known as Newton Road. That is the road that goes from Haverhill, Massachusetts over the border and up through Plastow and up toward Newton. A little bit closer of a view shows one other thing. Very heavy rainfall. Watch the storm. This graphic showing when the storm is at its most intense and had the heaviest amount of rainfall, which then collapsed into a downdraft, a concentrated downdraft known as a microburst. And those are usually very dangerous. The wind collapses. It's a big cool pool of air in the clouds itself, and it collapses, falls down toward the ground, and as it hits the ground, it spreads out in all directions, and that creates straight line winds going out in all directions. Another close-up look at the area yesterday, seeing that rain and very heavy rain move on through, and we'll pinpoint exactly the moment that that happened right about here between 3:35 and 3:45. You can see this heavy cell right here pushing its way toward Route 108, and the winds coming into that are what caused certainly some strong gusts, but then the collapsing air coming down out of the cloud is what was that microburst. So that's a wrap-up on the events of yesterday between about 3:30 and 3:45 in the Plastow area.
Hello and welcome to the Monsoon Safety Awareness Week series presented by the National Weather Service and Flagstaff. Today's topic is downburst winds. Strong storms during monsoon season sometimes produce strong wind gusts which can be damaging. We call these winds downburst winds, which are created by rain-cooled air that, upon reaching the ground, spread out and produce intense winds and sometimes cause damage. Depending on the size, we can call this a microburst or a macroburst, depending on if the area of high winds is small or large, respectively. These winds are different than those observed in tornadoes in that they spread out in a straight line. However, they can be just as damaging, with winds exceeding 60 miles per hour. The strongest microbursts have even been known to produce winds in excess of 100 miles per hour. A downburst is just a very strong downdraft from a thunderstorm, and particularly strong thunderstorms are often accompanied by these types of winds. When forming in dry environments, common in Arizona early in the monsoon season, we sometimes observe what is called a dry downburst, which would result in very strong winds but little precipitation. Alternatively, when the atmosphere is moist, a wet downburst can occur, with intense precipitation accompanied by strong winds. Downburst winds are especially common in the lower elevations in the desert regions, where drier conditions below the cloud layer can lead to the formation of intense downdrafts. However, they can happen anywhere in northern Arizona. Sometimes these strong winds can be visible by dirt and debris being blown around near the ground, or by what we call a gust front, which is a smooth, linear type of cloud that forms immediately ahead of the strongest winds. In this video, you can see the gust front pushing overhead right before it starts to rain, and the winds becoming very gusty. Stay tuned for tomorrow's topic of dust storms, and be sure to find us on Facebook, Twitter, or YouTube. Thanks for watching.
During the evening of August 24, 2011, an outflow boundary pushed westward across Tampa Bay, interacting with the west coast sea breeze, causing thunderstorms to develop. One of these storms over Old Tampa Bay showed a classic downburst signature with winds spreading out rapidly, as seen in this animated image from the Terminal Doppler Weather Radar located at MacDill Air Force Base. Within the white circle, you can see the winds moving away from the radar, the yellow areas, and toward the radar, the green and blue areas. According to the Doppler radar estimates, the wind speeds going away from the radar are briefly as high as 50 to 55 knots at around 250 feet above the ground, along the coast of Pinellas County near Weeden Island. This downburst can also be seen in this reflectivity animation, but it's not nearly as obvious as in the velocity data. You can see how the shape of the rain area becomes rather circular as the wind spreads out in all directions.
Weather forecasters currently rely on ground-based observation networks to provide real-time lightning monitoring. Coverage gaps over land and sparse non-uniform observations over oceans, however, limit the application of these networks. Additionally, the national-scale ground-based networks in the Western Hemisphere detect only cloud-to-ground lightning strikes, missing cloud-to-cloud lightning, which poses the greatest risk to aviation. Also, since cloud-to-cloud lightning typically precedes the occurrence of cloud-to-ground lightning, ground-based networks are limited in their ability to offer early warning of an approaching lightning threat to those on the ground. The next generation GOES-R weather satellites will monitor all lightning activity across nearly all of the Western Hemisphere in real time, providing forecasters with a revolutionary tool for improved nowcasts and warnings of lightning, hail, and other thunderstorm threats. The next generation GOES-R satellites will carry the Geostationary Lightning Mapper, or GLM, instrument, which will continuously measure all lightning activity, cloud-to-cloud and cloud-to-ground flashes, across most of the Western Hemisphere. This will be one of the first instruments of its kind to simultaneously cover such a large geographic region. In addition to monitoring lightning in real time, These satellite-based lightning observations will help improve predictions of tornadoes, hail, microbursts, flash floods, and help provide warnings of an impending cloud-to-ground lightning danger. The GLM's continuous observations will help forecasters predict and track severe thunderstorms and related hazards including lightning, tornadoes, hail, microbursts, and flash floods across nearly all of the Western Hemisphere. Information provided by the GLM, which includes total lightning flash rates and trends, is expected to improve tornado warning lead time, as well as nowcasts of hail, downbursts, and microbursts. It can do this owing to the correlation between observed trends in lightning activity, thunderstorm updraft and downdraft strength, and subsequent severe weather.
Well, there's a new high-tech help to keep you and your family safe in a storm.
Storm 5 meteorologist Bree Smith has the latest on a revolutionary new weather satellite.
That's right. How you see weather in your home is all about to change. Now, currently, your weather satellite data comes from 2 satellites 22,000 miles up. The newest and most sophisticated satellite to date is here. Meet UCAR. So what's with the funny name? GOES stands for Geostationary Operational Environmental Satellite. R is just its place in a series. It's a satellite parked in the same spot that orbits in time with the Earth, watching over us all the time. What makes GOES-R so special? On board is a powerful new tool called the Advanced Baseline Imager. It will produce 60 times more data, seeing severe weather where you are 5 times faster and 4 times clearer. Pole-to-pole scans will go from 27 minutes to just 5. Also on board, the GLM, Geostationary Lightning Mapper, a first-of-its-kind lightning mapping system that not only maps lightning as it hits the ground, but lightning within the clouds. Mapping lightning allows us to see severe weather forming more quickly. This 6,000-pound powerhouse is our newest set of eyes in space, working faster and seeing things more clearly and more often. Faster data means better lead time for tornadoes and severe weather. Clearer data means more accurate information. The next generation in weather satellites is here. GOES-R just launched this past weekend and is currently making its journey to orbit. Once it's in place, we're going to bring these images to you as we track the threat of severe weather right here in Tennessee and all across the country. This is so exciting.
Wow.
It launched at 5:42 on Saturday after an hour delay. There were some last-minute technical issues, but they were able to get it off the ground in that satellite window. And this is absolutely going to revolutionize how we track severe weather for people at home. It's very exciting.
All right. Thank you, Bree.